guess I wasn't clear.
Observations of NEAs, and so I'm going to show you our end results and conclusions thus far. The motivation for this project was to learn more about the OH and H2O content of near-Earth space, and it was previously thought that objects in near-Earth space that didn't have atmospheres would be nominally anhydrous because of their increased temperature at formation and their low perihelia. However, in 2009, multiple missions discovered a 3-micron feature on the moon, and in 2012 discovered a similar feature on Vesta. On the moon, the 3-micron feature is believed to have been caused by hydrogen implantation due to the solar wind, but on Vesta it's believed to be from carbonaceous material influx. In 2018, Rivkin et al. Determined that the two largest NEAs, Ganymede and Eros, also have a 3-micron feature, and the delivery of that material was also likely due to the solar wind. For our project, we used IRTF SPECS near-infrared spectrometer, both the PRISM and LXD short mode. We conducted 43 observations of 29 NEAs, so we have multiple observations of several of our targets. After observing and downloading the data, we process the data using the SPECS tool package, and then we use a NEADM to remove the thermal tail. So in this plot on the right, with reflectance versus wavelength, the black data points are the original data, the blue are the thermally corrected data, and the red line is the reflected continuum. For this particular asteroid, 2000 WO107, it does not have a 3-micron feature because the blue data points lie along the red reflected continuum in the 3-micron region. So this asteroid does not have OH or H2O on its surface. However, we've determined that 4 of our asteroids do indeed have a 3-micron feature. Ganymede and Eros were observed in this project as well, and were also seen to have a feature just like in Rivkin et al. We also determined that 3122 Florence has a feature. And most recently in 2020, we observed 1999 AP10 and determined that it also had a shallow feature in the 3-micron region. We also have several NEAs with a potential 3-micron feature. These objects have a higher degree of noise in the spectra, but if you use a 2 sigma error, you can see that the band is still there. So 1627 IVAR, 2004 JN13, 2014 JO25, 1998 XB, and 2002 PZ39 round out our collection of NEAs that look to have a 3-micron feature and OH or H2O on their surface. So the next question is, what drives OH and H2O delivery and retention? If it is the solar wind delivering H ions and creating OH and H2O on the surface, one might think that all of the NEAs studied would have these features. However, that's not the case, so something must be controlling the delivery and or the retention of this material. One thing that we determined after processing all of our data is that there are multiple band shapes in our collection. So band shape type 1, which is exhibited by 3122 Florence, 433 Eros, and 1627 Ivar, is a wide linear feature similar to the sharp feature discussed in Takir and Emery, 2012. These asteroids are all about 4.5 kilometers or larger in diameter. Their perihelia are greater than 1 AU, and they're all S-types. We believe that the volatile composition is pure OH, as a sharp linear feature has been confirmed to be due to OH on multiple other papers. And these objects, we believe the solar wind delivered this OH delivered the H to make OH via hydrogen implantation. Band shape type 2 is possessed by 4 NEAs, 1999 AP10, 2014 JO25, 1998 XB, and 2002 PZ39. These NEAs have a narrow and flat feature compared to the sharp linear feature of the previous NEAs. These NEAs are all less than 2 kilometers in diameter. Their perihelion is about 1 AU or less, and most of them are Q-types or something similar. JO25 is an SR type, so it doesn't quite fit the same compositional trend as the others. We believe the volatile composition present on these asteroids is a mix of OH and H2O potentially, as a more bowl-like feature seen in Takir and Emery 2012 is indicative of the presence of H2O. So we believe this might be a mixture of the two materials. We think that to some degree solar wind hydrogen implantation is still the main cause for this feature, but another process such as recombinative desorption might be forming water at high temperatures when these objects are near perihelion. Sorry. Finally, the third band shape is possessed only by 1036 Ganymede, and this is considered to be a wide, flat, or bowl-like feature. Ganymede is an SR type with a very large aphelion of 4.08 AU, which means that it easily reaches into the outer main belt of asteroids. Interestingly enough, when compared to a spectrum of Vesta taken in this study early on, we see that the band shapes are actually quite similar. So we believe that the delivery mechanism might actually be similar as well. So we think that Ganymede likely has a 3-micron feature due to the influx of carbonaceous material on its surface. And being that it can go all the way into the outer belt, this seems likely as well. In conclusion, we've observed 29 NEAs, and 4 of those have a feature, and 5 potentially have a feature. That leaves 20 other NEAs, 9 of which do not seem to have a feature, and 11 have too low of signal-to-noise ratio to really make a determination. We have 3 band-shaped types that seem to indicate something about where the OH or H2O came from. Type 1 is composed of large, high-Q S-type NEAs, and we believe the OH is from the solar wind. Type 2 is composed of smaller, lower Q NEAs, and seems to have a mix of OH and H2O from solar wind hydrogen implantation. And finally, type 3 are possibly V or R type NEAs, such as Ganymede, that have OH and H2O from carbonaceous material influx. Thank you very much. Please feel free to email me if you have any questions or discussion points. I apologize that I couldn't be here in person to field your questions, but I would love to talk to you via email or some other mode. Thank you again.